Hi, today we're going to talk about integrating powers of trigonometric functions. And so to start, you might look at a power of trigonometric function and you might think, oh, maybe I should do a integration by parts. But it turns out the integration by parts doesn't quite work out like we would hope. In particular, if I've got, say, powers of cosine squared, or say cosine squared, if I split off one of the cosines as the u and the other one as the dv, well, when I differentiate and integrate that thing, I'm going to end up sort of getting sines out of this. And so it's not going to work out that I can do a u substitution after a while. So instead, we have to do a little bit different thing. And in particular, you have to go back to your trigonometry and actually use your trigonometric identities to get these things to work out. So in particular, there are two identities that we really want to use, actually four identities that we want to use. The first are the half angle identities. So there's one for cosine and one for sine. And then there's the Pythagorean identities. And the half angle identities that we want to use are a little bit different than maybe you've seen in your calc or in your trig class. So in your trig class, you probably had like a sine squared of an x over 2 or an angle that's half of an angle, or you might have just had like sine of half an angle, and that was equal to square root of some stuff. So what we've done in this one is we've actually said, okay, so let's make it a little bit easier to deal with, and let's just look at sine squared and cosine squared of x. And so what you sort of can see here, our half angle formula says if I've got sine squared, that's the same as 1 minus cosine of 2x over 2. And if I've got cosine squared, that's 1 plus cosine 2x over 2. And so to remember this, remember that they look very, very similar. In fact, they look almost the same, except that minus in there. So the way that you sort of maybe want to remember this is that sinus is minus. So the sine term leads to the minus in your 1 minus cosine of 2x over 2. That's one way to sort of remember this. All right, so once I transform into this, I can actually now integrate cosine of 2x using a substitution u equals 2x. And so what I would do is if I'm integrating this thing, I would integrate, 1/2, and I would have minus cosine of 2x over 2. And I would say, oh, okay, so I can integrate these things separately. So that's just 1/2 x. And then I do a u substitution where u is 2x in here. And then du is just 2 dx. And so what I end up getting here is actually like a minus, it'll be sine of u over 4, which is really sine of 2x over 4, and then plus a c. So to integrate this thing with the cosine of 2x, I basically think of it as a chain rule. I integrate the cosine back to sine, and it gives me sine of 2x over, in this case, 4 when I've got the denominator. Okay, and it might be necessary to do this more than once. So it may be necessary to sort of introduce this, and then you square this thing out, and it gets sort of bigger and bigger. And now I've got a cosine squared of 2x in there. Then I apply the half angle formula again, this time with cosine squared of 2x in there, and then it becomes 4x in the inside, and then I kind of continually do this until I'm left with no more squares in my integration. Okay, so this works out pretty well if I've just got squares throughout, and that's the idea. The other identity we would potentially want to use here is, in fact, the Pythagorean identity. This is the one that most people remember. So the Pythagorean identity is sine squared of x plus cosine of squared of x is equal to 1. And it's the Pythagorean one because remember, it really comes from the triangle with a hypotenuse of 1. If we take the hypotenuse to be 1, the angle or the side lengths here are actually, sine of x is over here and cosine of x is over here. Okay, and then the sum of the squares of the two legs of that right triangle is the square of the hypotenuse. And the hypotenuse is 1, so that's 1. And then it's equal to sine squared plus cosine squared. And so that's the idea. So now, what I again want to do is get cosine squared out of there or sine squared out of there. And so I get cosine squared is 1 minus sine squared, or sine squared is 1 minus cosine squared. And then once I've done this identity, I'm going to do a u substitution with either u equals sine of x or u equals cosine of x in the integral. Okay. So now the question is, when do I use each of these things? So for powers of sine or cosine, the strategy for this is going to differ depending on the parity of m, the power. And parity just means, is it odd or even? So if it is an odd number, there's one strategy. And if it's an even number, there's another strategy. And there's also a nice general formula for finding these things. But I want to go through the techniques that I would do here, because now those general formulas don't help us if we're talking about products of powers of sine and cosine. So we can talk about the parity of the m, is it odd or even? And then we can talk about what to do in each case. So in the case that m is odd, I'm going to peel off one of the terms. So I'm going to peel off either a sine or a cosine. And that means that m minus 1 is an even number. And now I'm going to rewrite sine to this power as sine squared to another power. And that sine squared, then I'm going to replace with my 1 minus cosine squared. And then I do a u substitution where u is cosine. And you'll notice du is going to have a sine in it. And that's going to cancel. And so then I'm going to be left with a nice integration with u in it. And so that's a nice thing. Same thing for cosine. This time I peel off one cosine. And then I'm going to use a u substitution on sine, because I'm going to replace this with 1 minus sine squared. Okay, so we rewrite that power as m minus 1 over 2 as the exponent of sine squared, which is 1 minus cosine squared to that same power, or 1 minus sine squared to that same power in the other term. Then I do a substitution with either u equals cosine for the first one, or u equals sine for the second one. And then it's going to give me my term that I need. So let's do an example of this, because I think that's the easiest way to see it. So I cosine to the 5th of x. So 5 is an odd number. I want to peel off one of those cosine terms. So I've taken my sort of cosine x out, and now I want to split that even power into cosine squared to some other power. So it's going to be cosine squared squared in this situation. Now I replace my cosine squared using the Pythagorean identity. Cosine squared of x is 1 minus sine squared of x. So that's going to give me that. Now I FOIL that 1 minus sine. Well, actually, really now I do a u substitution. Let u equals sine of x. Derivative of sine of x is cosine of x. And so I'm really going to get 1 minus u squared squared, integrate with respect to u. Okay. So this is really nice. So now I just integrate each term separately. I FOIL this thing out, integrate each term separately. And that's going to give me this. So I get u minus 2/3 u cubed plus 1/5 u to the 5th plus c. And now since u is sine, I replace all those with sine. So I have sine of x minus 2/3 sine cube of x plus 1/5 sine to the 5th of x plus c. And now you'll notice this is sort of messy. And I can always go back and check that I actually have the right thing. So I differentiate this term. So if I differentiate that thing, I should get cosine to the 5th of x. And it turns out that I actually do get cosine to the 5th of x out of this term. Okay. So with an odd power of sine or cosine, this is not too terrible. It becomes sort of a u substitution. Maybe the bad part is going to be here, because I've got to do like a big power of 1 minus u squared, which is kind of a pain, but it's just algebra. And so that to us is basically just an, okay, I can do that. It's just, if I had to, I could, right? So that's the idea. So now, what about an even power of sine? Well, unfortunately, with an even power of sine or cosine, well, I cannot peel off and do this u substitution trick. So instead, what I have to do is I have to do sine squared to the m over 2. M is even here, so m over 2 will be a nice integer. And so then I can now replace sine squared using the half angle formula instead of the Pythagorean identity. And so the half angle identity, I replace them. So that sine squared becomes 1 minus cosine 2x over 2, all raised to the m over 2. And then the cosine squared would become 1 plus cosine 2x over 2. And then I raise that thing to the power that I have. Again, in this situation, this is going to be where the tricky bit comes in. That is going to be a algebra problem, right? So you're just going to take a power of 1 minus cosine of 2x over 2. And so you just raise that to that power, meaning you multiply it by itself. It's going to be a FOIL. And so you're going to be multiplying, a whole bunch of binomials together, and then you end up with something in the end. Well, unfortunately, in the end, what I might end up with is something with a cosine squared of 2x in it. In that situation, then I have to use the half angle identity again, this time for cosine squared of 2x. And so it'll be 1 plus cosine of 4x over 2 in that situation. And so at that point, we use our algebra to evaluate this thing and then go from there. So let me give you an example of this. And this is, it can be very tricky the higher the power of sine or cosine we have. So in this situation, sine to the fourth of x is really sine squared squared. Okay, so that's the idea. I sort of break this up and put a sine squared raised to another power, sine squared raised to, or cosine squared to another power. And that since it's even, that's going to be possible. So now what do? Now I use the half angle formula. So the half angle formula is 1 minus cosine 2x over 2. And again, sinus is minus. So the sine squared goes to 1 minus cosine of 2x. Okay. And so now what do? What we're going to do next is take that power. So I exponentiate things. So square the denominator becomes 4. Square the numerator, it becomes 1 minus 2 cosine 2x plus cosine squared 2x. And if you don't remember how to do this, it's important that you do. So we have to actually write 1 minus cosine of 2x multiplied by 1 minus cosine of 2x. And so I FOIL this out. The first terms give me 1. I get 2 cross terms. Both are cosine 2x, and they're both negative. So I get minus 2 cosine 2x. And then I get a cosine squared of 2x is the last term. They're all still over 4 because the denominator went to 4 when I squared it. And then I go from there. So now after this, I look at this last term again, cosine squared of 2x. Now I again have to use the half angle identity for this. So cosine squared of 2x is 1 plus cosine of 4x. So I double the angle inside divided by 2. And so this whole thing here is replaced with this. And so then what are we left with? So I can integrate each one separately. That's fine. And this last one here, I've got this 1/4 times that thing that I had as the cosine squared of 2x. So using that half angle formula for that and integrating the first two is not too bad. 1/4 is just 1/4 x. Cosine of 2x, again, is a u substitution. U equals 2x. It gives me sine of 2x over 4. In this case, because the 2 gets multiplied by an extra 2 from inside. So the inside function in my u substitution gives me a 2 in the denominator, and then I go from there. And then I'm left with this. And now I integrate this last term. So again, I have to do a little bit of work here, but it's not too bad. So the integral splits into the integral of 1/2, which is 1/2 x, and the integral of cosine 4x over 2, which is cosine of sine of 4x over 8. And now I multiply all of that through, combine all the like terms, and what I'll get is 1/4 x and 1/8 x is 3/8 x. And then I have a minus sine of 2x over 4, and then plus sine of 4x over 32, because 4 times 8 is 32, plus constant c, and that's how I end up with what I need. Okay, again, I can double check. When I take the derivative of this thing, I should end up getting sine to the 4th of x. Now, in this situation, what we're going to get is not going to be exactly sine to the 4th. It's going to be something in terms of this half angle formula. So in particular, we'll have to go back and just reverse that half angle formula in order to actually reverse both of those half angle formulas in order to get back to sine of the 4th of x. So it's not clearly exactly the same thing. It's going to be a little bit harder to see it as we're differentiating this thing. Okay. And remember that differentiation step is not necessary. It's just sort of the double check your work kind of step that you can do. And we're lucky that we can do it because it's sort of nice to be able to differentiate. That's something we can do pretty easily, straightforward, works out nicely in most cases. So now what about products of these two? So in the case that I have a product of sine and cosine, again, it's going to depend on the parity of m and n. So what are they? Are they even? Are they odd? If one of those two is an odd number and it's positive, a positive odd number, I can peel off that term, replace the remaining terms, which is an even number, using the Pythagorean identity, do the u substitution with that non-peeled trig function. So in the case that I peel out one of the signs off, I do a u substitution where u is cosine, and then I kind of work from there. And then I integrate with that. If both of them are even, then I have to rewrite both of them using the half angle formula for each. So in the case that both m and n are even, cosine squared, sine squared times sine squared of x times cosine squared of x, I would have to rewrite both of them using the corresponding half angle formula. In the case of a square, it's not so bad, but if it's fourth or sixth or eighth or something like that, it's going to be pretty tricky. So then I go from there. All right, so let me give you an example of this. So I want to integrate sine cubed of x cosine to the minus 2 of x. And that is a power minus 2 power, not an inverse anything. That is the negative 2 power. So that's really secant squared of x inside there. And so I can integrate this. So what do? I peel off one of the sine terms. So I peel off sine. And it gives me sine squared of x cosine to the negative 2 of x in times sine of x equals integrated with respect to x, right? Now, I replace sine squared with 1 minus cosine squared. So that's the Pythagorean identity. Then I multiply that cosine to the minus 2 through. I get sine is 1 minus cosine squared. So I get 1 minus cosine squared times cosine to the negative 2. The cosine of the negative 2 is multiplied by 1. Cosine of negative 2 times cosine squared is just 1. Integrate with respect to x. Then I've got a sine x left over. Now I make the u substitution. So at this point, I'm going to let u equal cosine x, which means that du is sine x, really negative sine x, cosine, negative sine x times, dx. Okay, so now what do I get? So I make that u substitution. I get 1 minus u to the negative 2. And I think I have the wrong. Yeah, so it really should be a negative of that whole thing. And now I want to integrate with respect to u. So what I will get, this is going to again be negative u minus negative 1 u to the negative 1, which is just negative u plus 1 over u plus c. Again, this is negative cosine plus 1 over cosine plus c, which is just negative cosine plus secant plus c, which is minus cosine x minus secant x plus constant c. Okay. So there we go. So we have a minus missing there. It should be a minus in there. That comes from my u substitution in here. Oh, I'm sorry. No, I did the right thing. Sorry. Let me back up for just a second. So my u substitution worked okay. I just swapped my two terms here. So when I put a minus in front of this thing, it makes it 1 minus 2 u to the negative 2. And so it actually works out. Integrate this thing. I should end up with just cosine of x plus secant of x equals plus c, right? Okay. Again, I can differentiate this thing. And when I differentiate cosine of x plus secant of x, I probably, again, end up getting this thing where it's 1 minus cosine squared times cosine to the negative 2 or times secant squared. And then I can sort of work with that as it comes to this, the Pythagorean identity. And so I can use the Pythagorean identity to work this. All right. So in order to ease the workload for some of these things, in particular the powers of sine, cosine, tangent, and secant, I have reduction formulas. And so these reduction formulas, a lot of them come from just a sort of straightforward integration by parts And so you can sort of do an integration by parts to get this reduction formula. And I'm not going to show you that now, but it's how it works out. So if I have sine to any power, I can rewrite that as, in the integral, negative sine to the n minus 1. So that's that power minus 1 times cosine of x all over n, plus n minus 1 over n times the integral of sine to the n minus 2 over of x, integrate with respect to x. And you can imagine how this would be useful. So if this power is like 5,000 or 15, bigger powers, you can sort of reduce that power down by 2. And then I can run the same thing. I can actually do a reduction formula on that integral as well to get it down even further. And so I can sort of use the reduction formula over and over again until there's something in there that I can integrate. Okay. Now the reduction formula just takes a little bit of practice to sort of work with and get to work. So you just have to work through it and do some of the problems with it. And you can sort of see the cosine one looks about the same without the minus in front of it. And again, you can sort of see why that would be. And then the tangent, so the tangent is a little bit different. It's tangent 1 away from the exponent and then 2 away from the exponent in the integral. And I forgot an x in there for that tangent one. So there you go. So this one should have an x in here, right? And then the secant, again, this one's actually even a little bit more different, but it's not surprising really, because the derivative of secant is secant tangent. So you sort of get the secant tangent coming into this, pick up an extra tangent as it were, and then you can kind of go from there. All right. And I'm missing a sign in here as well, so just be aware. There you go. And these reduction formulas are in your book, so you can find them in the end of the book. There's kind of a last several pages of this thing that has tables of integrals in it. And those integration tables, a lot of them have these, well, all of them from the book have these reduction formulas in them as well. And so you can sort of get the nice version of it from there. And I'm going to try to make one of these for you as well as a handout to just post online. I'll post it onto my math lab as sort of a way to not have to sift through the book yourself. So I'll sift through it for you and grab it and put it in there. All right, cool. So the reduction formulas are great. Again, it doesn't work if I've got products of these things in there. So in particular, for tangent and secant, using the reduction formula is kind of the way to go. You do that if you can. And if it's secant squared, then I know that it's tangent. Like, in other words, I have an idea. So what I'm going to do next is I'm going to say, what about products of secant and tangent? So we're going to use the same types of rules for products of tangent and secant. Again, it depends on the parity of m and n. Are they even? Are they odd? If n is even and positive, then what I've got is some power of secant squared. Now that secant squared, I'm going to peel off a secant squared and then rewrite that even power of secant using the Pythagorean identity for secant, which is secant squared is 1 plus tangent squared. And that one, so that Pythagorean identity comes just by dividing sine squared plus cosine squared equals 1 by cosine squared. So cosine squared of x, 1 over cosine squared of x is secant squared of x, and cosine squared over cosine squared is 1, sine squared over cosine squared is tangent squared. So dividing that is where we get this extra Pythagorean identity out of here. And then I make a u substitution where u is tangent. Okay. Same sort of deal if I've got an odd number. So if tangent is raised to an odd number and n is any number bigger than 1, I'm going to peel off a secant and a tangent. So peeling off a secant and a tangent, I can rewrite the even power of tangent now using the same sort of identity. This time it's tangent squared equals secant squared minus 1. Just solve the previous one for tangent squared. And then I substitute u equals secant x, because the derivative of secant is secant tangent, which I have as one of the thing I split off. So when I do that u substitution, I'll have the derivative of it in there. And so I'm allowed to do that. And then finally, if I have an even tangent power and an odd secant power, I cannot do either of those previous tricks. So the previous tricks rely on secant being to an even, so that I can do this sort of secant squared bit, or tangent being to an odd, so I can take a tangent and a secant off and do a tangent squared substitution. Instead, what I'm going to do is I'm going to rewrite the power of tangent using the tangent squared. That's going to give me a polynomial in secant. And it's not going to be a nice polynomial in secant, but that's the idea. But each one of those terms is a power of secant of x. So I'm going to apply the reduction formula for powers of secant to each term in my polynomial. And I'm going to apply it as many times as I need to the point where I can take the integral that I have. And so that's the idea. So you just continually take this integral or take the reduction formula and reduce the powers of secant down to the point where you can take the integral. That's how we work from there. Okay. Let's try an example. So I've got tangent cubed secant to the fourth. You'll notice that this actually follows both of the rules that I had before. So I could use either n is even and positive, n in this case is 4, or m is odd and positive. In this odd and positive. So in this case, m is 3, which is odd and positive. So I can do either one of these. I'm going to do the secant one. So I'm going to peel off secant squared, and then I'm left with secant squared. So, you know, I've sort of peeled off one of my secant squareds. That's 2 of the 4. And I'm left with secant squared. I make my substitution for secant squared. That gives me 1 plus tangent squared times tangent cubed times secant squared. Make the u substitution for u equals tangent. Du is secant squared x dx. And so I'm left with u cubed plus 1 times 1 plus u squared du. So that u substitution got rid of all of the terms there. Now I have u cubed plus u to the 5th, which is u to the 4th over 4, u to the 6th over 6 plus constant c. Now u is tangent. So that means the integral here is just tangent to the 4th over 4 and plus tangent to the 6th of x over 6. So tangent of x to the 6th over 6, tangent of x to the 4th over 4. And then all that plus c. Okay, so this one, it turned out to be a little bit nicer. And in particular, I actually find that the tangent secant ones do end up being a little bit nicer. Usually it's just a u substitution. The worst ones here for us are the ones where we have to use the half angle formula. So the half angle formula is not like the go-to formula. The go-to formula is going to be your Pythagorean identity. And then you're going to try to do a substitution using that Pythagorean identity. Okay. The same kind of rules will apply to powers of cotangent and cosecant, with the exception of some of the signs. So if you think about it, when you do this substitution where tangent and secant, when I do the u substitution, the derivative of tangent is secant squared, whereas the derivative of cotangent is actually negative cosecant squared. So I'm going to pick up a minus in my u substitution in the cotangent and the cosecant situation. And then the last thing, the Pythagorean identity we use here when we're doing things with cotangent and cosecant is going to be cotangent squared plus 1 equals cosecant squared. So you can develop these rules for cosecant and cotangent. So if I go back to these rules again, if I have an even positive number and I've got a cosecant there, it's going to be cosecant squared is going to peel off. I'm going to rewrite that in terms of cosecant, written in terms of cotangent squared, and then I'm going to substitute u equals cotangent x. And derivative of cotangent is negative cosecant squared, so I pick up a minus in that u substitution. Okay, and again, if m is odd and positive, again, I split off a cosecant cotangent, and then I have the even power of cotangents that's left as cosecant squared minus 1. I make my substitution u equals cosecant x, and then derivative is negative cosecant cotangent, so I pick up a minus in my u substitution. Okay. And then finally, if they're both even and positive and odd and positive, then I'm going to rewrite this using secant. The cotangent squared is cosecant squared minus 1. And then I produce a polynomial in cosecant of x. Then I apply a reduction formula to each term using this cosecant reduction formula, which I haven't given you. It's actually going to be on the sheet that I give you. So the cosecant squared one is on that as well. Okay. So what I want you to do is get in there, try this out. They do take a little bit of time, so just be aware it's going to take some time to do these things. Get in there and try it now and see how it goes.